Hello everybody, here Saber Said is speaking. I'm gonna to present today my work about role of spatial variability of soil resistance in longshore variability of coastal barrier response to super storm surges. I did this work in collaboration with Niels Gosberg from the same institution, and I'm going to speak divide my speak into six parts. Part is the introduction, problem statement, objective methodology, results, and then the conclusions. Um, as we know, due to the climate change, extreme storm surges may become more intense and frequent. As a result, our dunes, our and barrier islands function as defense element against such storm surges and coastal flooding. However, they can be uh, they can breach and the probability of breaching may increase with climate change, as we see here in the photo. And the research question of this work: how can most probable breaching location be predicted? So the problem statement is related to the flow velocity. As we know that flow velocities during storm surges are quite high, and state-of-the-art prediction models for dune erosion and breaching like XBeach is based on conventional sediment pickup function that overestimate erosion volumes during such high flow velocities. Therefore, artificial limiters, as we see here in the photo, are often used in order to limit the model behavior during high flow velocities. One of them is to use artificial limiter by limiting the active shield parameter at 1, and this limiter was suggested by McCall 2010, and the second, which was suggested by me, is to increase the critical shield parameter using an amplification factor until it fits with until the predicted volumes, erosion volumes, fits with observed volumes. So the breaching process based on that needs to be studied considering the longshore variability and the role of barrier soil properties in erosion. So the objective of this study is to distinguish among different forms of alongshore variabilities and to present some extensions of the XBeach model in order to account for special variability of soil resistance to erosion and to apply such new extension of XBeach to a real case study. As we see here in the figure, when we, in order to quantify the vulnerability of a dune system or a barrier island, we consider two things. First, the load, and considering also the period, the wave climate, including the period, the wave height, and the direction and the tide level. This is, I call it here, the hydraulic loading. And the second thing which we always account for is the topography, bathymetry, and self-dimension of the barrier. When we study the interaction, or most of the state-of-the-art studies are based on considering the interaction between the loading and the topography. And this frame, which was suggested by Mickey and others in 2018, represents the state-of-the-art approach used to assess the vulnerability of dunes. So the methods of this work is to add an extension of this framework and to implement it in the XBeach model, as we see here in the photo, in order to account for the soil resistance R, so that all soil properties can be mapped and included in the analysis of dune erosion and breaching. In this case, this soil purpose can be included based on the dilatancy theory of Vanry 2010, which account for the dilatancy based erosion at high flow velocity regimes, and it's based on amplifying the critical shield parameter based on the permeability and porosity. We did these extensions and we applied it to a case study, and this case study, as we see here, is considering a barrier island which is consistent of a berm and then a dune, and it's assumed that it is especially uniform along shore in terms of dimension and the bathymetry. Then we apply a hydraulic load consistent of surge levels that takes this form and reach to 6.6 meters. Besides that, we apply sometimes long crested waves and sometimes short crested waves, which has properties of HS equal to 1.75 and TB equal to 6.6. Both loads are applied using the Jones swap. So in the first case, we are not considering the directional spreading of waves when we would like to generate long crested waves, and in the second case, we consider the spreading of waves, and in order to study the interaction between the longshore variability of the applied load and the longshore variability of the soil properties, as we will see. So here we are considering that permeability is varying along shore at the dune location along shore, as we see here in this photo here. We say that the permeability we are assuming it at the middle of the case study with high value that reached to 45 meter per day, and then we reduce the permeability here in these two locations, and then we assume uniform permeability with very low value all over the model, as we see here in the photo. So as you have seen here in the animation, we can find that the dune is eroded and we have a breach at the high permeability zone, and then the sediment deposit here behind the dune. So this means that erosion varies. We will find also that erosion varies along shore based on the permeability value, and a breach is taking place at a location of higher permeability. As we see here, this is again to say that the permeability is varying along shore, and the breach is developed at the location of higher permeability. So here we see the variation. This is a cross shore direction. This is a long shore direction cross section, showing the variation of the permeability with the erosion, with the breaching development. We say that the breach is developed mainly at the location of high permeability. So, and at zones of low permeability, the erosion volumes reduce significantly due to the dilatancy reduced erosion regime. Here we see some cross sections from section X1 to X5, and we find that at section X1 and section X5 we have the same erosion, and this is very few. It's less than other erosion at other cross sections because of the high permeability, the very low permeability, and then at section X2 and X4 we will find that we have more erosion because of the higher permeability, and then we find that at the middle, at section X3, we have full breaching here, as we see here. This is due to the higher value of permeability. Then when we apply now the short crested waves combined with the surge tide level, we will find that okay, still the erosion is varying along shore based on the permeability value, but instead of having one breach at the middle, we have two breaches with smaller sizes. This is because of the interaction between the short crested waves and the barrier topography. And the hydraulic load. This means that the breaches are still taking place at the location of high permeability, and the erosion is varying also alongshore. This means that directional spreading of wave and subsequent longshore variability of loading produce less erosion and multiple breaches, but breaches still take place at high permeability zones. So here we study the effect of porosity, and we compare the same case study previous results when the porosity was 0.4. Now that we reduced it, we assume that porosity can decrease under compaction or consolidation, and this might strengthen the barrier against coastal erosion. And here, this is the reason why we reduced the porosity to 0.3, and we found that when we compare both, that the erosion is decreasing a lot, especially at the location of higher permeability, and at the locations of less permeability, we will find that porosity has no effect. So the reduction of porosity increases the soil resistance to erosion and reduce breaching size, but at locations of very low permeability, the reduction of porosity has no effect. The conclusions from this study is that at a high flow velocity regime, sediment staining is no longer a grain by grain pickup, but it is determined by dilatancy, reduced erosion, permeability of barriers soil determines at a large extent the degree of soil resistance to erosion, especially during high flow velocities. The XBeach code is extended to account for spatially varying soil properties, and then we will find, based on this extension, that the most probable breaching location can be determined when soil properties are considered in the analysis, besides the longshore variability of the applied load and barrier topography. Then the reduction of soil porosity, either by mechanical compaction or consolidation, increases the soil resistance to erosion, and as a recommendation based on this study, that the reduction of the barrier permeability and over the porosity represent a naturally based solution and suitable structural measure to reduce coastal erosion, particularly during extreme storm surge.